Again, good morning, and let's continue. So in a previous class, we discussed interference. Basically, if you have two identical waves, again, it means the same amplitude, the same period, the same frequency, and the same wavelength. If they sort of interact, we can say that they interfere. They will interfere, right? Giving us spots with large amplitude, where amplitude is doubled, and spots with zero amplitude, constructive and destructive interference, right? We derived everything, analyzed in the previous class, but we haven't looked at the problem. We started looking at this problem, but we did not finish it. So let's finish it. So we derived this condition. So if you look at 2 pi divided by lambda, which is the wave number, you remember, multiplied by the path length difference. What is path length difference? It's just an additional distance that, for example, the second wave has to cover relative to the first wave to reach the point in question which you analyze for constructive or destructive interference. And then delta phi naught, it's the inherent phase difference. It's just the initial phase of the second wave minus initial phase of the first wave. And information about the inherent phase difference you can get either if initial phases are given, then you can just subtract them, or reading the problem carefully. If the problem says out of phase, like in our case, it should tell you immediately that these two waves, okay, that the inherent phase difference is pi. If the problem would say two identical antennas, or in phase, okay, that should tell you immediately that those waves, okay, the inherent phase difference is 0, right? So in our particular case, so we have 2 out-of-phase radio antennas, so the inherent phase difference in this case is 0. Delta phi naught is 0, right? So again, that comes from those words. And again, let me refresh the situation. So we have our introduced coordinate system, and we have 2 radio antennas. One is positioned over there, radio antenna number 1, positioned at the point 300 meters. Origin is over here. And then symmetrically, we have second antenna at position at the point minus 300 meters. Okay, and like we discussed in the previous class, what happens physically? So this antenna creates its own circular waves spreading all the way to infinity, right? So I can draw wave fronts, right? This creates its own circular waves spreading all the way to infinity, so I could draw wave fronts, but probably I will skip it. We've done it in the previous class, right? And so, of course, you can walk here in this field with antenna, right, receiving detecting the net radio wave, right? So here you can have, for example, somewhere maximum constructive interference, then again destructive, then again constructive, destructive, constructive, destructive. You can move there, farther away, again constructive, destructive, constructive, destructive. Pretty much this whole field will be filled with C, D, constructive, destructive, constructive, destructive, right? So the problem asks, what about this particular point P, which coordinates of which is 300 and 800? So basically this point, somebody standing with an antenna, right, detecting the net wave, right? So just in front of the first antenna, right? Okay, so effectively nothing but analyzing this condition. So we need to find delta R, delta phi naught we already discussed. Out of phase, and I wrote 0. Why? Come on, guys. It's pi. And you didn't say anything, and you haven't started screaming at me. It's just what I had in the previous, okay, from the previous recitation class. Out of phase, pi. And you sort of silently listening to me, right? I'm still human. I can say something and I can write something else occasionally. Of course, not very often, but occasionally it happens, right? But you should feel confident to say, come on, what you wrote doesn't make any sense, right? So pi. Right? So now next step, delta r, right? So delta r. In order to find delta r, we need to draw r2 and r1. r2, it's a distance from the second source to the point in question. r1, it's a distance from the first source to the point in question. So what about r1? r1, from the geometry, you can see immediately, it is equal to 800 meters because the point P is right in front of the first antenna. So I can write that r1 equals to 800 meters. Now, what about r2? r2, Pythagorean theorem. Because this triangle, this point, and that point, it's a right triangle, right? So this angle is 90 degrees. So this distance, this side of the triangle is 300 plus 300 is 600, and this distance is 800. Simple Pythagorean theorem. No one should have any problems over here. 800 to the power of 2 plus 600 to the power of 2 and square root. 64 plus 36, it's 100, right? And then tons of additional zeros. And then if you take a square root, it's 1,000 meters. So R2 is 1,000 meters. So delta R is obvious, 200 meters. So this minus that, so delta R equals R2 minus R1 equals to 200 meters, right? 1,000 minus 800, 200 meters. So then, what's next? So we found this, we found that. So now lambda. There's the last unknown, right? So how can we find lambda? Wavelength. And again, these waves are identical. Frequency is given 3 megahertz. Again, it means that this source generate radio wave with 3 megahertz, and this source generate radio wave with 3 megahertz. So it means the wavelengths are going to be the same. And again, remember, these are radio waves. It means that they propagate with the speed of light. All right. So remember, if you have problem has a radio wave or it says electromagnetic wave, it should tell you immediately the speed of light 3. Okay, the speed is the speed of light. And again, don't make another silly mistake, because quite often a few students on the final exam, if the problem is about sound waves, they still use speed of light. When you see that, it looks so, it doesn't look good, right? So if it's a sound wave, usually I give the speed of sound, right? It's usually about 340 meters per second, give or take, depends on the temperature, depends on conditions, right? But usually 340 meters per second, but not speed of light. Don't make those, that silly mistake, really silly mistake. Right? Okay, so speed of light is given, so we know, so we can use lambda f. Of course, in this case, it will be the most convenient. And so we can get what we need. We need wavelength. So it will be c divided by f. So c, it's a 3 times 10 to the power of 8 meters per second, divided by the frequency 3 mega 10 to the power of 6. You remember it. At this point, probably you remember. Sooner or later, you will remember all these prefixes. Hertz is just 1/2, right? Just a fancy name for this 1/2. Seconds will get cancelled, and we will have 100 meters. Yeah, it's quite a wavelength, but we're dealing with radio waves, so radio waves can have long distant wavelengths, long wavelengths. Okay, so now we're all set. Now we just write this condition and see, are we going to get this or that? So let me, okay, I will put a bullet of 2 pi divided by lambda. Lambda is 100 meters. Then delta r is 200 meters. And plus inherent phase difference is pi. Okay, so now we just need to add this and see which condition we're going to get. We will get 2 times 4 pi, times 2 pi 4 pi plus pi 5 pi. And now we have to be careful. Usually when we have normal classes, when we are at school, right, at this point I would usually bug students. Okay, tell me your conclusion or your conclusion. Are we going to get constructive or destructive or something in between, right? I usually bug several students, and I'm telling you, lots of students in the first time they came up with the wrong conclusion. When they look at this, oh, it looks simple. It's a constructive interference. Plenty of students give me this answer usually, constructive interference. But let's analyze. Be careful at this point. Look, for constructive interference, we have pi times 2 times integer. 2 times integer. It doesn't matter which integer you have, odd or even. If you multiply it by 2, you're going to get, of course, an even number. You can have, for example, 2 pi, 4 pi, and so on. Every time for constructive interference, this must be an even number times pi. We have 5 pi. It's impossible to have constructive interference, right? Because 5 is an odd number. But 2 times m, it's all the time even number. Make sense? Right. Don't make those silly mistakes. So at this point, don't rush. Carefully look, right? And to avoid mistakes, right? Okay, definitely not constructive interference. I hope you agree with me, right? So now let's see, we're getting destructive interference. So let me rewrite this condition over here and figure out which m can fit this, because you remember we can have tons of constructive spots and spots with destructive interference. And again, each of those spots can be described by a particular m. You remember m goes from 0 to infinity. M, this integer, right? It's not mass, it's not nothing like that, it's an integer, right? So m plus 1 over 2 and times 2 pi. And again, remember, m, it's a 0, 1, 2, 3, and so on. So let's see which integer fits our condition. So m equals 0, so it's a 1 over 2 times 2 pi. It's a pi, not our case. M equals 1. 1, it's a 2 over 2 plus 1 over 2. It's a 3 over 2 times 2 pi. It will be 3 pi, not our case. M equals 2. 2, it's a 4 over 2 plus 1 over 2. It's a 5 over 2 times 2 pi. It's a 5 pi. Yeah, m equals 2. That's our case. Right, so that's m equals to 2 in order to get 5 pi. So obviously, that's where, at that point P, we're going to have a destructive interference. Again, very common place for mistakes. When students get to this, they feel very excited, problem almost done, and they rush and they write wrong conclusion. Okay, so that's it. And again, sometimes it can be speaker number 1, speaker number 2, generate acoustic waves, exactly the same story, except for, of course, read the problem carefully in order to figure out what's the story with the inherent phase difference, delta R, and analyze the conclusion. And of course, don't use the speed of light with the sound waves, acoustic waves. But otherwise, mathematics is exactly the same, right? Quite often, problems like this I give on the final exam. And most of the time, students do well on the problems like this. Of course, if students don't come to classes. All right. Okay, so if you have any concerns, questions, right, say it. Otherwise, we will move to this problem. And mainly because of this problem, I postponed homework. So what do we have here? It's a problem 27 from chapter 17. This problem is from chapter 33. It's about light. Right. I think from chapter 33. Okay. So we have two circular waves. Right. You see, source number 1 generate this black wave. Source number 2 is over here, generate this blue wave. And this blue and black wave are shown with circles. You remember? We discussed these circles. Basically, these circles, we call them as a wave fronts. These are wave fronts. In the previous class, we discussed it. And wave fronts are collections of crests. Right? So wave crest, trough, crest, trough. So these are collection of crests. And so then, you remember again, there are two types of graphs which can be used to draw them. It's either history graph or snapshot graph. This is obviously a photograph of two waves. It's a photograph, basically distribution of waves frozen in time. So it's a snapshot graph. These are, again, every time, like in the previous section, I made a mess in this particular snapshot. It's a snapshot graph, right? So, and then if I draw, you draw the wave, for example, over here, these crests and troughs, right? So first, over here, it's you are on the line, so it's a crest, right? Then between lines, of course, you must have trough, right? So crest, then trough, then again crest, then again trough, then again line. It's a crest, right? And of course, it's a snapshot graph. The distance between adjacent crests is a wavelength. So wavelength, right? Then, what about the blue one? It's exactly the same story, right? Again, so wave fronts. So again, we have crest, then trough, crest, and so on, right? So now, in order to analyze certain spots about constructive and destructive interference, we have to use, again, the same condition, like what we used here. Physics, again, not physics, of course, the nature of waves is different, right? Mathematics is the same. Mathematics is the same, right? So, and we're going to analyze 3 spots: P, Q, and R, right? So, are we going to see constructive or destructive interference at those spots, right? So, again, we will have to analyze delta phi naught, delta R, maybe wavelengths, we'll see, right? Okay, let's start with the inherent phase difference. And that's the major issue. Right? So let's discuss. So you have to be careful and look at the diagram properly, diagram in the book or in Mastering Physics. And if you look at the diagram carefully, you will see that, of course, this distance must be equal to that distance because these are wavelengths, right? Wavelengths doesn't change, at least in our cases, as the wave propagate, right? So the distance between adjacent wavefronts must be lambda. So lambda, and now let's see what is happening near the source in terms of crest or trough. Because basically I'm trying to figure out what is the story with the inherent phase difference. Okay, so in order to do that, so again, here we have the crest. So it's a wavefront, it's a crest. And then if you look carefully again in the picture, this distance equals to that distance. At least I try to do it. I try to draw it that way. I try to do my best. Slightly, of course, not absolutely correct, but my intentions was to show that this distance between these two adjacent crests and this distance are the same. So it means what? It means that if we have crest here, then on the way to the source, we should be able to reach the trough and then again reach the crest. So at the source of the first wave, we have a crest. All right? Right? Because again, if this distance equals to that distance, so over here there must be a crest. So I can draw something like this. So for the first wave, so I said crest, right? So you're going to see something like this. And this is the point where the first source is. So we're basically getting cosine function. At this moment of time, because you remember it's a snapshot graph, it's a photograph of the wave, okay, two waves, at a certain moment of time. And now I just drew sort of like a cross section. So at the source we have crest, so here crest, then trough, it's this trough, and then this crest is over here. So that's the first source. Now let's draw the same for the second. Let me switch to blue, because now it's a blue source, right? So, right. And now let's analyze the second one. Again, these two waves are identical. So here we have wavelengths, and of course here we have between the blue wavefronts also. Wavelength, wavelength. Okay, I can show it here. So again, it's a wavelength, wavelength, right? So now let's again, so we have crest, trough, crest. And now again, according to the picture, if you look at the picture carefully, the distance from the second source to the adjacent, to the nearest crest, this distance. And these distances, and these distances are the same. It means that over here, from point 2 from the source to the nearest crest, also wavelength. So it means that if we have crest here, then we should be able to reach trough, and then again crest at the source 2. We're getting crest. So it means that blue wave behaves in exactly the same way, right? So we're going to see something like this. So they overlap. So we have basically here cosine function, and here cosine function. So we don't have to shift them by any distance in pi in order to overlap. Sources are identical. So what can you say about the inherent phase difference? 0. Right? If we had here, for example, let's say sine function instead of cosine, the inherent phase difference would be pi over 2. If instead of cosine function over here we had minus cosine function, inherent phase difference would be pi. But in this case, by just looking at the picture, we came up to the conclusion that the inherent phase difference in our case is pi. So let me write. So delta phi naught equals to pi. Again, from the figure, just by looking at the picture carefully, right? Okay, before I go into the analysis of those points, let me emphasize immediately, discuss problem from your homework. You're going to see something similar in your homework, problem 28, except, so the first source is going to generate exactly the same wave with the same wavefronts. But the second source story is slightly different. So in the second source, lots of mess over here, right? In the second source, look, this distance between this wavefront and this wavefront, of course, it's a wavelength, right? So here, it's a wavelength. So we're reaching crest, then trough, then crest, and the distance from the source to the nearest wavefront is this distance, you see this distance, is half of that distance, half. So it means that if this is lambda, then this distance, okay, let me show it over here underneath, is lambda over 2. Again, if you look at the picture in Mastering Physics or in the book carefully, you will see that this distance is half of that. It means what? It means this. So if we are reaching, not if, we're reaching crest at this wavefront, and then we have enough distance only to reach the trough. So at the source 2, we have a trough. Here we have, you see, we had crest because this distance was equal to that distance between the wavefronts, but now the distance is only half a wavelength. So it means that from this crest, we could reach only the trough at the source. So in this case, I can draw, so we're going to have, for the second source, you see, second source, we have trough at the source, and then something like this, right? So you see we have minus cosine function. Here we had cosine, you see it started from the trough, away from the crest, right? And then trough is only here. But now at the source we have trough and then on the crest. So this is a minus cosine function. And the first source is exactly the same like in the problem which we're discussing now. So we have and this is wave at the moment of time when the snapshot graph was sort of taken. So we see we have cosine function and minus cosine function. What's the inherent phase difference? Inherent phase difference, pi. These two sources are out of phase. Out of phase. It's like here. It's here. Right? Pi, out of phase. So here we can write that delta phi naught equals to pi. So that will be the story in your homework problem 28. Okay, so now let's go back to 27 and finish the rest. If I don't discuss this in the class, I get tons of emails from students why mastering physics doesn't accept my answer, because they usually assume that the inherent phase difference is 0. But in this case, it's pi, right? Okay, so be careful in your homework. So now back to problem 27. In our case, so delta phi naught equals 0, so we can dump this, right? And as a result, our condition can be simplified, right? So if this is 0, then 2 pi here and 2 pi here and here can be canceled, right? And our condition will be easier, right? So the inherent, or I mean delta r, so it will be m times lambda for constructive interference, m times lambda for constructive interference, and delta r equals m plus 1 over 2 lambda for destructive interference. So now, for this particular case, of course, condition is simpler. But again, it's only true when delta phi naught is 0. So you cannot write this condition for problem 28 because your inherent phase difference is not 0, it's pi, right? Okay, so yeah, as I told you, so we need to analyze these 3 points. So let's do it. And the problem says, create a table, this table. Probably I will write the table here. P, Q, and R, 3 points. Oops, I can do better. And R. And, yeah, and here above, probably. First column, let me write the inherent phase difference. Although in the book, this column is not added. I added this column. Right. So inherent phase difference. Then we will have to find R2. Right? R2 is inside of this delta R, inside of delta R. Then R1. Wait, R1, I said R1 and wrote R2 still. Right, R1. Right. Then delta R. And then conclusion. Are we going to get constructive or destructive interference? So in your homework, again, in problem 28, you will have to create a table like this. Okay, fill out the table like this. Inherent phase difference, let me write immediately, of course, 0. It doesn't matter which point you analyze, inherent phase difference, it's a property of two sources. It doesn't matter which point you're looking at. P, Q, or R, or any other point, inherent phase difference will be exactly the same because that's property of the system. That's why it's called inherent. Right? But again, in problem 28, this column will be filled with pi, 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 pi. So R2, again, R2, it's a distance, just normal distance from the second source to the point in question. So let's start with point P. So R2, and we're going to write all these distances in terms of lambda, wavelength. Because again, you remember the distance between two adjacent wavefronts is wavelength, lambda. Right? So R2 for point P, so here 2, source 2, right? And here's the point P. So we need to write this distance. This is R2 in terms of lambda. Right? And again, remember, since sources are the same, so this lambda, blue lambda, and black lambdas are the same because all these conditions were derived assuming that we have waves with the same wavelengths, the same frequency, right? So this is R2. So in terms of lambda, it's a 1 lambda plus 2 plus 3 plus 4. So this distance R2 is 4 lambdas. So over here, I can write 4 lambda. So distance in terms of wavelength. So 4 times lambda. Now let's do the same for R1. R1, it's a distance from the first source to the point in question. So 1 wavelength, you see, 2, 3. So we're looking now at the black wavefronts. So what? 1, 2, 3, 3 lambdas. Right. So 3 times lambda. Okay, so now what is delta R? Of course, just lambda. It's a R2 minus R1. So lambda M, of course, let me again remind you that here M equals 0, 1, 2, 3, and so on, right? So in our case, for point P, M equals 1, and we're getting constructive interference, right? Constructive interference. Right. So it means that we're going to have constructive interference. There is an easier way of getting to the conclusion almost immediately. Look, at the point P, we have black line intersect blue line. Again, what does it mean, that line? It's a wavefront. It's a collection of crests. So it means that we have at point P, we have black crest. And on top of that, we have also blue line, blue crest, right? So we have crest over crest, condition for constructive interference, right? Crest over crest, constructive interference. And that's what we got using our condition and analyzing this delta phi naught and delta R, right? But again, by just looking at the picture, you can answer it. So now let's analyze point Q. Point Q, where is Q? Here, Q. So R2. R2, it's a 1 wavelength, 2 wavelengths, 1 and 2. 2 lambda. 2 lambda. Right? Yeah, 2 lambda. Now black from the first. 1, 2, 3, and now we have half. So point Q is between wavefronts, black wavefronts. You see, point 2 is between black wavefronts. So we have, it means that 1 wavelength, 2, 3, and then half a wavelength. 1, 2, 3. So it's a 3.5 wavelength. So over here, 3.5 wavelength. 3.5 lambda, right? Okay, so if you subtract, and just look at the absolute value, right? You can, in this case, subtract R1 minus R2, right? So we are going to get what? 1.5 lambda, which is 3 over 2 lambda, right? We can write it as a ratio. So it will be 3 over 2 lambda. Okay, obviously it's not constructive interference. 3 over 2 lambda you can get out of condition for destructive interference when m equals 1. M equals 1, so it's a 2 over 2 plus 1 over 2, it's a 3 over 2, 3 over 2 lambda. So here, destructive interference. And again, let's run that simple analysis about crest and troughs. Point Q. Point Q is on the wavefront, on the blue wavefront. So it means that at point Q we have blue crest. But black, in black, relative to the black wave, it's between the wavefronts. So it is in the trough, black trough. So we have blue crest, black trough. Of course, they're going to destroy each other, kill each other, right? Giving us destructive interference. Whenever you have crest over trough, complete cancellation, right? So, and now the last one, R, point R. So now you're familiar. So what we have, blue, 1 wavelength, 2, 3, and then half, because it lies between blue wavefronts. So it will be 1, 2, 3, 3.5, 3.5, 3.5 lambda, right? And black, 1, 2, and again half. It's between the two black wavefronts. So it's a 2.5 lambdas. 2.5. 2.5 lambda, right? So now subtract them. 3.5 minus 2.5, of course, you're going to get lambda, which is integer number of lambdas. So it's a constructive interference. So we're going to have constructive. So now, again, in terms of those crests and troughs, so point R, it's a black trough between lines, and also blue trough. So trough over trough, it's again constructive interference. Trough over trough, it's like a crest over crest, right? The same story. So of course, constructive interference, constructive interference. But of course, if you have crest over trough, it's a destructive. But in our case, our point R is at constructive interference. Okay, makes sense? And again, be careful. These conditions, simplified conditions, cannot be used for problem 28. Because again, we rewrote this more general condition in this form because the inherent phase difference was 0. But in your case, inherent phase difference is going to be pi, right? So you'll have to analyze this. So you'll have to find R2, R1, delta R, plug it in this with delta phi, yeah, and calculate what you're going to get, constructive or destructive interference. Okay, so of course homework will be slightly, but not significantly, more complicated. Okay, makes sense? So if you don't have any suggestions, questions, okay, if you do have, of course, ask them. Now we can switch to interference of light. Actually, this was also light, right? But low frequency radio waves. We usually don't call that light. This light, this radio waves, low frequency electromagnetic waves. Okay, so I should be able to erase. I hate erasing it, but I have to do it. So now interference of light, basically double slit experiment. We discussed it in the lecture. So now we just need to look at, okay, a review and then look at the problems. And of course, we will continue it on Wednesday. Wednesday will be the last recitation class. Right, so double slit experiment. Right, interference of light. Okay, let me draw the picture. Yeah, we'll start probably here. Okay, slit number 1 and slit number 2. Maybe I should label them. Yeah, let me call this 1, 2. And of course, we need to illuminate it with a laser light. The source must be more or less monochromatic, right? Single frequency. Right, so let's say. So we have some wavelengths, some frequency, so everything is given. And the distance between these slits is d. And so what happens in terms of physics? Since the size of the slits are more or less comparable with the wavelengths, so these slits on this side of the screen are going to produce us some kind of circular waves. Okay, let me draw something like this. Right. And this slit is going to behave in exactly the same way, producing its own circular waves, right? Like over here. But of course here, okay, maybe these were, I know, the waves on the surface of a lake, right, or something like this, right? Here, it's a light. The only difference in the nature of waves, right? So, strictly speaking, if somebody asks you, what about this point? Are we going to have constructive or destructive interference? Of course, you can apply this condition. Look at the inherent phase difference, R1, R2, and you should be able to answer the question. So, from the point of view, from a mathematical point of view, we're not looking at anything new. It's exactly the same. Those two conditions must be applied over here. So from the mathematical point of view, physical point of view, the story is exactly the same, right? For example, at this point, I can tell immediately that we should have a constructive interference at this point, right? Because we have basically, according to my picture, I have crest over crest because we have an intersection of two wavefronts, right? So we should be able to answer any question about any points of this. But from the practical point of view, from point of view of an engineer or experimentalist, right? So this system can be used, for example, theoretically in a spectrometer, for example, right? To measure the wavelengths of an unknown source, for example, unknown laser. And it must be more practical because the problem is you don't see visually these bright and dark spots, right? You have to basically somehow run there with the source, with the detector in order to detect are you going to have constructive or destructive interference, right? So from the practical point of view, it's not very convenient because this pattern is not visible. So as a result, as any practical experimentalist, of course, you have to come up with some practical solution. And they just put a screen over here. Oh, too light. Why it's not giving me a solid? Okay, screen. And in order to observe those bright and dark spots on the screen, right? Okay, and of course we can draw the center of the system. And of course on the screen you're going to see what is called interference fringes, right? At the center of the screen all the time you're going to have bright spot, then dark spot, then again bright spot, bright, dark, and so on. And the same story on this side. So you're getting what is called interference fringes. Again, it's just that these are the constructive points of constructive and destructive interference, but now you can see them on the screen. That's it, right? For example, if I position over here the screen, right, I will see something like that. And, right, of course, for example, if this is the, let's say, bright spot corresponding to m equals 0, this corresponds to m equals 1, this m equals 2. On this side of the screen, the same story, m equals 1, then m equals 2, and so on, m equals 3, right? So position of those bright spots can be defined either using, maybe I should use now a different color, this angle, theta, in this case it's a theta 2, or dealing with angles are not very convenient, right? Again, since light is not visible, just you need to scatter it with something. So it's better to use, instead of angle, use the distance along the screen. So if I introduce y-axis, then this is 0, y equals 0. Then this point is y1, this point is y2, and so on, right? So it's easier to deal with these distances along the screen. So distance from the center of the screen to the bright spot which you want to analyze, right? And we derived these distances, right, in the lecture. So those distances, y sub m, m can be again 0, 1, 2, and so on, equals to integer wavelengths times distance. LL, it's a distance from the double slit to the screen, that distance L. D, it's a distance between the slits, lambda L over D. So this is basically the formula that you have to use, nothing else except for this simple formula to find position of the bright spots, again measured from the center of the screen. Okay, it should be enough for a review. And another thing, guys, for a double slit experiment, this distance between, for example, these two adjacent bright spots, these, any two adjacent bright spots, the distance is exactly the same. So all these bright spots are equally spaced, right? So sometimes it's good to remember to be aware of that, in order to simplify solution of the problem. Of course, sooner or later you will get by yourself to that conclusion. Right, okay, so double slit, and now let's start looking at the first problem. Most likely we will have to continue it next class. So this is chapter 33, problem 1, I think, yeah. 33.1. So double slit, and what is given? Double slit illuminated with two sources. How much time we have? Okay, probably I will just, what's the time? Okay, 1 minute. So I'll have to restart the problem next class. Again, so we have, let's say, yeah. So we have double slit, all right, and it is illuminated. Okay, I will just explain in words, and then we will continue next class. Illuminated with two sources, two laser lights. One is orange. The second one is unknown. Two lasers, one frequency of which is known, the second one is not known. Then, of course, here there is a screen. Right? You see these dark and bright spots. So now we have two sets of different fringes. One corresponds to orange, right? You'll have orange, bright, dark, bright, dark, bright, dark. And then that unknown, right? And also, somebody noticed that a bright spot of orange light the third bright spot of the orange light overlap with the fourth. So the third and the fourth bright spot of an unknown light, they overlap. So basically they're at the same point, for example, over here. So using that information, of course, the wavelength of the orange light is given, we should be able to find the frequency of an unknown laser. Basically, a spectrometer, all right? So this device can be used to measure the frequency of an unknown source. Okay, so we'll finish this next class. So we will have to discuss problems about double slit and diffraction grating. So that will be on Wednesday.